Lithium is one of the softest metals there is. You could cut a piece with a butter knife. And yet, inside a solid-state battery, that same soft lithium cracks a ceramic far harder than itself, splits it wide open, and shorts the whole cell dead. For years, nobody could agree on how something this soft breaks something this hard. A team in Germany and China just watched it happen.
Here is what you are looking at, in plain terms. A solid-state battery swaps the flammable liquid inside a normal lithium-ion cell for a solid ceramic. Do that well, and you get more range in the same space, better safety, and faster charging. That is why car makers keep promising it. The catch is this exact failure. When the cell charges, lithium can grow thin metallic fingers, called dendrites, that push into the solid electrolyte until they bridge the two sides and short it out. So dendrites are the gate. Control them, and solid-state batteries can finally leave the lab in volume. That is where this new result matters, and it is worth being precise about how big a deal it is. It does not hand anyone a finished battery. What it does is settle a stubborn argument about why the ceramic breaks at all, which is the thing engineers have to know before they can design around it. The work comes from the Max Planck Institute for Sustainable Materials in Düsseldorf with Shanghai Jiaotong University, led by Yuwei Zhang and Gerhard Dehm and their colleagues. It was published in Nature in April 2026. The title is dry, but the claim is bold. Lithium penetration in a garnet electrolyte is driven by mechanics, by pressure, not by leaking electrons. To catch the failure in the act, the team built a deliberately simple test. The electrolyte is a garnet ceramic, a lithium lanthanum zirconium oxide doped with tantalum, ground into a disc about 150 micrometers thick, roughly the width of a sheet of paper. Instead of a full sealed battery, they laid the parts out flat and used a sharp tungsten needle as one electrode, so a single lithium dendrite would grow straight across the surface, where they could see it. Then they nudged it with a small voltage, about 50 millivolts, close to how a real battery actually operates. Now, the argument this was built to end. Everyone agreed dendrites are the problem. The fight was about the physics. One camp said the metal is basically born inside the ceramic. Electrons leak along the boundaries between grains, meet lithium ions already in the material, and grow fresh lithium nuclei deep inside that later link up into a short. The other camp said something more mechanical. Lithium plates into a crack that is already there, gets trapped, and pries the ceramic apart from the inside. Telling those two stories apart is brutally hard, and that is why the debate ran for about a decade. The answer lives at the tip of a lithium-filled crack, just nanometers wide. But lithium is light, reactive, and so fragile that an ordinary electron microscope beam can create lithium out of the sample and fool you into seeing nuclei that were never there. Warm it, expose it to air, and the evidence rearranges itself. So they froze the whole problem in place. Every step, cutting, imaging, mapping, happened under vacuum at about minus 190 degrees. At that cold, the beam stops making phantom lithium, and the real distribution holds still. They sliced needle-thin samples right at the dendrite tip with a focused ion beam, then imaged where the lithium actually was, atom layer by atom layer, with cryogenic electron microscopy and a technique that maps lithium specifically. And the picture was decisive. Right at the crack tip, lithium filled the crack completely, all the way into the sharpest point, with no gap left behind. But about 1 micrometer ahead of the tip, where the leaking electron theory said fresh lithium should be nucleating along the grain boundaries, there was nothing. No lithium buildup. No isolated nuclei at the junctions. The metal was only ever where a crack had already opened for it. There was one more trap to avoid. In a single flat slice, Some lithium pockets look like separate islands, exactly what you would expect if they had nucleated on their own. So the team rebuilt the crack in 3 dimensions, slice by slice. Those apparent islands turned out to be branches of one continuous connected dendrite, just caught at different depths. Nothing was born in isolation. It was all one intruding finger of metal following the cracks. That settles the fork for this garnet. The lithium is not appearing inside the ceramic on its own. It is plating into cracks. Which brings back the real puzzle. If lithium is just soft metal sitting in a crack, why does the hard ceramic lose? The answer is confinement. Out in the open, lithium relieves stress by flowing. It deforms and gives way. But packed into a crack narrower than it can escape, it cannot flow. So the pressure has nowhere to go. The team checked this directly. They mapped the crystal structure inside the trapped lithium and found almost no distortion, the fingerprint of metal that is being squeezed evenly from all sides rather than deforming. Their models put that internal pressure around 600 megapascals, thousands of times atmospheric pressure, pushing outward on the crack walls. Here is the part that makes it click. Garnet, like most ceramics, is strong when you push on it, but weak when you pull it apart. The trapped lithium presses outward, and that outward push translates into a pulling, tensile stress in the ceramic around the crack tip of about the same enormous size. The Max Planck team compared it to a jet of water cutting through rock. The lithium does not stab through like a needle. It pressurizes the flaw until the brittle ceramic tears ahead of it. And you can see the ceramic losing in 2 different ways at once. Some cracks run along the boundaries between grains, the weak seams. But about 1 in 5 grains cracked straight through the middle, through solid crystal. That mix matters. If leaking electrons at grain boundaries were the whole story, cracks tearing clean through the grains would be hard to explain. The pressure story explains both. And the fitted models say the grain boundaries are roughly 3 to 5 times weaker than the crystal interior, which is why cracks so often veer onto them. So the mechanism is settled, at least for garnet. Now the useful part. Knowing the enemy is pressure inside a crack tells engineers exactly where to fight. 3 directions fall out of it. First, make the ceramic itself tougher, especially those weak grain boundaries. The team found no sign of the tiny structural slips that let metals absorb stress, so the garnet just snaps. Strengthen the boundaries, for example by adjusting their chemistry, or give the ceramic some way to soak up stress before a crack runs, and it can resist that internal pressure longer. Second, and this one is counterintuitive, add deliberate flaws. If a crack is going to travel, you can shape the ceramic so it turns sideways instead of driving straight across to the other electrode. The team pressed small indents to seed transverse voids in a dendrite's path. When the dendrite reached them, it deflected about 45 degrees and followed a harmless sideways route, while the dendrite with a clear path kept going and shorted the cell. In their models, a round void lets a crack pass straight through, but a void stretched across the path steers it away. Third, stop the bad lithium plating before it starts, at the surface where lithium meets the ceramic. A thin protective coating on the lithium side can spread the current more evenly and keep metal from diving into flaws in the first place. That one attacks the problem earlier, before there is a pressurized crack to worry about.
It is worth staying honest about the edges of this. This is one specific family of ceramic, garnet, under carefully controlled conditions. It does not automatically speak for every solid electrolyte, and it does not declare leaking electrons irrelevant everywhere, only that they were not driving this failure here. It is a mechanism study on a model cell, not a finished battery. And the hardest case, stopping dendrites when a battery is charged fast and hard, is still open. The microvoid trick is a clever lab demonstration, not yet a manufacturing process for a separator thinner than a hair.
Still, the direction is clear. For a decade, the field could not even agree on what breaks the ceramic. Now, there is a direct answer. Soft lithium, trapped in a crack, turns into a pressure source that tears a hard material apart from the inside. That is the kind of result that does not make a battery by itself, but it tells everyone building one exactly where the wall is and gives them 3 concrete ways to start knocking it down.